figure out Blizzard had so many people leaving their servers that they removed the
Questions about the homework?
you can't delete your Blizzard account anymore.
Yeah.
So is anyone gonna ask questions? Yeah, today's 11/11, Veterans Day. The 11th month on the 11th hour.
All right. And if you have questions, I'll try to get to as many as possible.
Our teacher said it's for me to due date until Tuesday night. Actually, Saturday.
All right, they want the output voltage for this one. And I want to do it the standard way. And listen, if you just follow the rules, this is not hard at all. If you try to just memorize strategies for topology A, it's this, the output topology B, it's this, you'll get lost. There's too many possibilities. So I want to go through this one with you. First thing you always look for is going to be a voltage on one of these two terminals that's fixed. This one's obvious. We've got VS right here. Do you all agree with that, class? Once we have VS there, we know the voltage at one of the inputs is the voltage at the other. Correct, class? Does everybody understand that? So this is VS here as well. Nothing tricky about this. The same voltage at one terminal is at the other on the input. No current flows in to either of those terminals, and that's also critical. Now, if that voltage is here, that voltage is here as well, right? VS exists there, correct, class? And if VS is there, it means the current through that resistor flowing this way would be VS over R1. I didn't put the values in on purpose. I always recommend the last thing you do is put in the numeric values. Carrying numeric values through a problem oftentimes ends up causing you trouble. You'll drop a decimal point, there'll be something about that. Put those in at the end. Everybody got this so far? Now, if that current's flowing there, can any current come out of there? None. No current goes into or out of the differentials, right? The negative or positive inputs. Follow me, class? All the current has to come this way. And that current is this. It doesn't matter what you call it. I can call it I1. That is I1, right? Just take a moment. Make sure you see this. This should be very clear to you. Matter of fact, most engineers are, by their very nature, deductive reasoning people. You think through a problem based on the premises. What is true? And then you reason your way through it. So here, I know if that's the current through there, I know the voltage here, V2, which is going to be plus to minus, V2 right there is going to be simply I1 times R2. You all agree with that? Right. And then, since I1 is VS over R1, I can say that my V2 right there is going to be VS times R2 over R1. This isn't hard to see. Are you with me? Now, finally, to get this voltage right here, V out, is that what they're after? V out? All right, to get that voltage, just watch this. V out here would be equal to the, well, start at the ground point, right? 0. I go from 0 to up to here, I have VS, right? Y'all agree with that? And then from here to here, I have an increase of V2 or VS times R2 over R1. or simply Vs times 1 plus R2 over R1 is V out. And if they give you a value for Vs, you can get V out directly, correct class? If you have R1 and R2. That's standard. Here's the thing people do. This is a decoy. That's called a load resistor. That does not control that voltage, unless it's a short. But for any practical circuit, that would not have any impact on the output voltage. It's Vs, and the ratio of R1 to R2. Everybody got that? That's a straightforward problem. If you want, go ahead.
Yes, for B, what is the maximum current through RL, and then for C is the maximum current output of the outlet.
Well, it's the maximum current is just going to be the voltage V out right here, right, divided by R, whatever this is, RL, right? So if I want I this way, IL, I think this is a time domain. Does he have a voltage source that's like a cosine or something?
Yes.
All right, well, then IL, it would be in the time domain of T, is just equal to Vs, and it's going to be V out over RL. And that's Vs is what? Tell me what it is.
0.1 cosine magnitude 2000 T volts.
2000 T volts. And that's Vs, and it's going to be times 1 plus, what's R2 and over R1? I can't, it's what? I can't hear.
R2 is 3.8K and R1 is 200 ohms.
And what do you get when you divide those two?
1. Oh.
19.
19?
Yeah, out is just 2 cosine 2000.
So that means I have that, and I divide that by RL, and what is RL?
RL is 2K.
So by 2,000. So that's going to be 20. So it's going to be 2 over 2,000. That's 1 milliamp. 1 milliamp will be the max value. And it will have a cosine of 2000 T. Would be the time variation. The max is going to be just when cosine is 1. Follow me, class? I think that's the answer, but I don't know. I mean, that's it? Okay.
For B, that is correct. For C, C was where I struggled. What's the maximum current output of the op amp? And for that, you have 1.5.
Well, you got to understand something. That current's going through RL, but there's a current going here as well, right? All right, so that current we could calculate as well. Correct, class? You would just take V out. You take whatever this is, 2 cosine of 2000 T, and divide it by the series resistance added, because this doesn't have anything to do with shunting current. All the current must go down there. So you take V out divided by R2 plus R1 to get that current, and then add it to the actual load current. I mean the current in the load. You follow me? That'd be the output of the op amp. Yeah.
Can you explain one more time how we got the V naught is equal to Vs plus Vs R squared over, or R2 over R1?
Right. We did it this way, in a nutshell. Tell me what you don't see. Vs is there. Vs is here. Vs is here. The current here would be Vs over R1.
Right.
None of that current can come this way, right? Therefore, the current there is Vs over R1, right? Vs over R1 times R2 would be the voltage there, right? Therefore, Vs times R2 over R1 plus Vs would be the output voltage, right? It would be this voltage, which is Vs, right? That's Vs right there. Plus, then it would be the voltage increase here, which is Vs times R2 over R1, right?
Okay, that's it.
And then you would add them together. The only thing I did is factor Vs out in front.
Okay, that's it.
That's it. Got me on this one, class? This is a problem that makes you start thinking about secondary effects. Like how much current goes to load, then how much is shunted this way, what's the total output current from your op amps? It's making you, because there's going to be some limitations on operational amplifiers. I don't work with these all the time, but when you buy an op amp, it'll have a frequency rating that we'll get into later. It'll show you the amplification versus frequency, and it starts falling off. And you get something called the gain bandwidth product. You'll see maximum current on the output it can draw. All right, there's a certain limit to that because it'll burn up. You can't, if you draw too much, you basically burn the thing up. There's other limiting things that you'll become familiar with. But first and foremost, you gotta understand how these things work in the ideal sense. Then you work on the edges, the fringes. All right, another one. Nothing.
Could you do 17?
Yeah. The ones I gave you were pretty straightforward. They didn't have capacitors in them. We're gonna move into capacitors today and a few other things, but I wanna make sure that I'm clear on this stuff. So this is 17.
Yeah, 17 is really simple. Could you do 16 instead?
Well, since I can do 17 for you very quickly, I think, just to make sure everybody sees this once. This is 217. Here, they have just a 2-volt source. And they're sticking, I hope this is the same 217 as you're looking at. And they stick it into the plus minus terminal here. Then they have this going to here. And then they have an RL here of 2K. This is called a follower circuit. There's no resistor here, right? In your book? Correct, class? It's a short. Now, you, by this time, know the game. If there's 2 volts here, there's 2 volts here, right? And if there's 2 volts there, there's 2 volts here. Agreed? And if there's 2 volts here, there's 2 volts here. Agreed? And that means the current here is just its load is simply 2 divided by 2,000 or 1 milliamp. So now the logical thing you're thinking is why do you even bother putting an op amp there, right? Here's the reason, listen. What happens here is no current's being drawn from this source. This could be something that is got a very high internal impedance. That doesn't mean a lot to you. In other words, you can't get much power or current out of it. Something like a sensor. Y'all are, the MEs, I know you use all sorts of sensors, right? And the sensors will have an impedance, an output impedance that's listed. Well, that impedance a lot of times is very high. It means if you try to get any signal out of there, and you don't first use a follower circuit like this, you won't be able to get it because the thing will measure that signal have a much lower impedance. So all the actual sensor voltage will be it'll be developed internal to the sensor. Just try to appreciate what I'm telling you. So what this is, no current flows basically from this. Some does. It's called a trickle current, but it's in the noise. You don't worry about that. But what you end up getting is the same exact voltage as the input as you wanted here. And then now you have the ability to drive current and power. You can get a lot more power out of it. Because usually this 2-volt source, I'm going to just tell you the real truth about it. What he's trying to do is show you something that's real. Normally with a lot of sensors, they can be modeled as an impedance of maybe 5 mega ohms. And then they're going to have the sensor that creates the voltage. You would have plus or minus 2 volts. Now if I got 5 mega ohms there, and I'm trying to use this represents some sensor, if you can follow. But the way I need to monitor this sensor is with a 2K resistor. You see most of the voltages developed here. If you just put 2K down to ground and try to measure, you can't. So what you need is a follower circuit. Now in this circuit, no current could flow there, right? Right? So that 2 volts is right there. That 2 volts is here and here, and therefore now you can get a lot of current. You can get power, and it's measurable and it's usable. Follow me? That's a follower circuit. It's used all the time. Whenever you have something where you have a high impedance associated with any kind of a sensor, and you need to measure that voltage, remember this follower circuit. They're very useful all the time. You don't want to just amplify the heck out of it. You want to do this first, because this will get you what you need. All right. Now, next, another one. Yeah.
9.24.
Yeah. What are we ranking now, by the way? The rankings haven't come out. We're 13? What is Bama's 4? 4 or 5? I didn't think they'd fall too much.
Yeah, there's little in the way of us making it this year. There's little
For
in the
this
way of us
one-
making it this year. If Bama would have won, we could have used our previous way, even if we beat them in here. We beat the best team, but we didn't. Or at least they did. Oh, that's interesting.
Is this 4 volts here?
5,
And this?
4,
And this?
1200,
This?
4200.
And they want to be out? And they have a load there?
There's, yeah, 3K.
You don't worry about that. That's the last thing to worry about. It goes to ground. All right, this is standard. Again, the rules of the game are no voltage across the input terminals, no current into them. The inputs are with that minus and plus on the flat side of the differential amplifier. So if I come here, I know this is 4 volts, correct, class? Can you all see? That means that this is 4 volts as well, correct? Y'all with me back there? I don't know if you, whenever I see people looking on laptops, it concerns me. Yes? R1 is 1200. I wish you people would sit down close. R1 is 1200, but I'm not going to force you to. All right? Now, with that, if that's 4 volts here, do you all agree it's 4, right? Has to, because if you've got the voltage on one end, you got the voltage on the other. It's that simple on the input. If that's 4 volts and this is 5, there's 1 volt difference across there, right? 1 volt plus the minus 1 volt divided by 1200 ohms means this current, and I'll call it I1, is just equal to 1 over 1200 amps. Agree, class? Voltage divided by resistance is current. How many see this? You might be bored to tears because you see it so easily, but I gotta make sure you all see it. Can you see it, Isabel? Back there? And far back, can you see it? Far back, down at the laptop. Can you see it back there? All right, I gotta make sure. All right, now that current, problem's done. How much of that current can flow through here? Into the negative? None. It all flows around here. That means this voltage is what? That voltage is I1, right, times 4200 would be this voltage, call it V2, or it's 4200, right, times I1, or divided by 1200. 42 by 12, right? That's 21 by 6, right? And you can take it down. What's this value going to be of this voltage?
3.5 volts.
Is it 3.5, anybody?
Yeah.
That's 3.5 volts in the direction I've shown it, right? Now please watch this. I want to get V out now. Everybody with me so far? What I'm doing? You understand the reasoning, right? I'm simply getting the current through here, which is 5 minus 4, or 1 divided by 1200. That's the current, right? I use that current through here to get the voltage there, right? Now we're going to get the output voltage. I'm going to start at the ground. I get an increase of 4, correct, class? I got 4, no change here. Then I got a decrease of 3.5, correct? So my output voltage is 4 minus 3.5, or simply 0.5 volts. Do y'all agree with that? You with me on this one? This is not hard. And if you think it should be harder, it's not. It doesn't need to be. Now, once I have that voltage, if I want this current, what does it become? That current, I3K, is just equal to V0 over RL, or 3K, RL. So it's 1/2 divided by 3,000, or really it's going to be simply 1/6 of a milliamp. That's it. You agree? And that's, I think, the question, right? Isn't that what they asked?
I think the voltage across, the 3K resistor.
Well, that's just V out. That's 0.5. Right?
Something like 3.5 in the answer.
All right, well, wait a second, maybe there's something I'm not seeing.
It had all the lines are connected on the bottom.
It doesn't matter if they're connected like this, because that's what a ground effectively does. Now, I'm gonna tell you, just bear with me here. It's 1200, right? 1200 ohms, and this is 5 volts. Is the polarity positive there?
Yeah.
Is the polarity positive there on top?
Yes.
Well, that's 5 minus 4 is 1. 1 divided by 1200 is that current, correct? Now that current flows here. They might have just asked for the voltage across R2. That might be what they get. V out itself will be this. If I know that current I1 is 1 over 1200, right? 1 over 1200 times R2, or 3.5, is the voltage from here to here, right? Correct? Now, if I want to find the output voltage, I have to start here, right? I get an increase of 4, and then I get a decrease. Take a look at the signs, right? Decrease of 3.5. That leaves me with 0.5 volts. If they've got, is their answer say V out is 3.5 or something?
Yes, the answer is you posted.
What? Let's say again.
The answer is posted in the OneNote.
Yeah, what is it?
It's negative 3.5.
For this problem? Yeah. You can't even what? Well, wait, is this 4? And that's 4, right? Well, look, 5, 4, 1 volt, positive, current's flowing out. That's the right answer for this problem. Unless there's something I'm not saying, I'll have to look at this one.
I think I meant the water.
Huh?
I think something.
Now, if this was 4, this is 5, maybe a little, then you will get minus something. Then you will get that minus. Might as well do it that way for the heck of it. Let's make this 4 and that 5, all right? So this is 4, just watch, and this is 5. All right, now we're gonna take off all that other stuff. Just work with me on this one, guys. So now, what do you see happening? Well, if this is 5 and this is 4, that means there's a plus to minus 1 volt difference that way. Now the current has to flow that way, correct, class? The current would flow this way, and I'll call it I1, and I1 now would be equal to the voltage difference 1 over 1200 amps. Now that current would flow here as well. And if that's I1, this was 4200, right?
Yeah.
That would make this plus or minus I1 times 4200, or it would be 1 over 1200 times 4200, or 3.5 volts. Correct, class? Right? You with me? I'm just reversing. Now notice it's going to be plus to minus, right? Look at the direction of current. Correct, class? Now what's the output voltage going to be there? They have a minus? There you're going to get 5 here, right? And then you're going to get plus 3.5. That would be 8.5 volts in the output. I don't know, that there's something wrong about that answer.
Okay.
I'm not sure if that pertains to that problem or not. No, the first way I did it is, that's the right answer. I'm not sure about the answers, the solutions. Any other problems? Class? I got one for you then, and then before we're gonna do one more thing. Actually, we could do 27, not 27. It's very similar to what we just did. I'll do 27 first, and then go through what I've got in mind. All right, so for 27, you have a voltage here, plus the minus, then a resistor. Goes into an operational amplifier. Then you have another voltage. This is a class, these are kind of problems. What they're doing is they're starting to increase the level of complexity slowly. Not taking a giant step, but slowly. If you look here on this one, by the way, is this R1, R2 too? Is that right? All right, now watch. And reason it out. What are you looking for? The voltage on one of the input terminals, aren't you? That's the ideal. Sometimes you may have to, you're gonna have to actually calculate it. For this one, you calculate it. Now look, you all see this circuit right here, right? That is a closed, that's a series circuit. No current can flow into that positive terminal. Do you all see this, class? So that means the voltage right here with respect to ground, that voltage would be equal to V2 times R2 over R1 plus R2. Can you all see that? How many see this with me? Right? It's a series circuit. I want the voltage across this. So the voltage between here and here is just going to be R2 over R2 plus R1 times V2, right? And now it's over. Game's over. Because now I have the voltage here, and I can just call that V plus. That means I have V plus here, doesn't it? Class? You follow me on this, everybody? Yeah.
So, I thought that the voltage division, you did it over the sum when it was in parallel. Or is that for series?
Now, voltage division is always something where you take, just think of it, don't even, make it as easy as possible for yourself. How much current flows out of this terminal? Well, it would be V2, right, over R1 plus R2, correct? All right, that's the current, V2 over R1 plus R2. So what would the voltage be here? It would be R2 times that. So it's R2 times V2 over R1 plus R2. All right, the bigger the resistance, the more, in a relative sense in a series circuit, the more voltage you get across it. If they're parallel, the less current, right? So that's that voltage. Therefore, we know this voltage, correct, class? Are you with me? If we know that voltage, don't we know this current? Class? Sure, what would that current be? It would be equal to V1, right, minus V plus, which is that, over R1, correct? Correct, class? This is not a hard problem, you just reason it through. Now remember, V plus is that, V2 times R2 over R1 plus R2, correct? Now keep working on it. If I've got that current must go this way, right? Is this R2 here? All right, that means this voltage here is going to be that current. I'll call it V2 here, is going to be equal to I1 R2. I1 now is equal to this. So I can say it's V1 minus V plus. This is V plus, and I can put V2 times R2 over R1 plus R2 here. I have that. I should do it this way. Oops, sorry. So V2 minus V plus, which is that divided by R1 is the current. We take that and then we multiply it by R2. And now we have the voltage V2. Are you with me? How many see this right here? We're just going through the motions of finding the voltage, then the current, right? Now what would the output voltage be then? Take a look. Well, now, follow me. You can do this several ways. If I come this way, right, I get an increase of V plus here, correct, class? Right, so I'm going to have V plus, and V plus is this. If you want me to write it down, I will. So I have V2, right, times R2 over R1 plus R2. That's this voltage. No voltage difference, right? And then from here to here, what do I have? Well, it's a drop, isn't it, class? Y'all follow me? That's positive, that's minus, so it's minus that voltage. That's that voltage, which is kind of messy, but it's V1 minus V2 times the quantity R2 over R1 plus R2. And then it's divided by R1 times R2. And that's V out. Y'all follow me? How many see this right here? I know it's getting a little complicated, but now you can all see right here, you can do something. You can do several things. Once you actually take a look at this, we've got V2 here, minus a minus is plus, and then we've got V2 here, and we have R2 over R1 plus R2 that you can factor out of that one. Do y'all see that? Then you have V1 just by itself. I'm not trying to make this too complicated, but when you look at this V out here, it's going to be, now take a look at V1. It's minus V1, right, times R2 over R1. That's really the first term there. Then it's plus V2. Now here, that's a 1. When I factor out that, so it'd be R2 over R1 plus R2. Then it's times 1. And then I have minus is plus. I factored out the R2 over R1, so it's plus R2 over R1 here. R2 over R1. Y'all see this, class? And now, at that point, I think you could probably just call it there, but that is, does he have the answer in that form, or does he have it in?
So you're given V1, V2, R1, and R2.
You're given those values?
Yes, sir.
Then you have to plug them in. And, but that basically is how you do it. And again, the whole key to this thing, find this voltage from there, you got this voltage. Once you have this voltage, V1 minus that voltage is that current. Once you have that current, you have necessarily that voltage, and you can go through and calculate it. Yes, sir?
Could you explain why the voltage across the resistor is
You want to know why this voltage is here? Well, the voltage drop across here is between ground and this point, right? So the voltage here would be the voltage at the positive terminal, and therefore it's the voltage at the negative terminal. There is no voltage difference. If you can find the voltage here, you got it here. That's the bottom line. Agreed? All right.
So what is that resistor, how does that affect the whole thing, the one that's disconnected to ground?
This?
Yeah.
This causes this loop to allow current to flow, right? And this resistor, R2, develops the voltage that's going to be at the positive terminal, isn't it? Right?
So we have two R2 resistors?
They're the same value. They're same value. That's the whole principle. Yeah.
Would it also be possible to solve that by solving for current for that loop?
When you say that loop, do you mean this loop?
No, the bottom loop.
Well, once you get that current, right, you still need the voltage, right?
Could you multiply that current?
By R2. That's what we talked about a little bit ago when you asked me that question.
I mean, could you also multiply times R1 and V2 minus that resistor?
Well, you can take V2 minus R1 times that current to get this, but it doesn't matter how you get that voltage. You need the voltage at the positive terminal for this problem. Got it, everyone? Yeah.
I just had a question. Earlier we did a problem. The R1 was on the opposite side and it was going up to the top where that connection to V out is. So how come in that one we did V2 and it was just R2 over R1 instead of?
When they had a connection from here to here, it changes the entire dynamic of the circuit. Now, it doesn't operate like this one. The minute you take anything from the positive terminal to here, put a resistor, that's feedback. This is not a feedback loop. You've heard the term feedback, haven't you, class? All right, that would be a feedback. Go ahead.
Wait, so you start with the voltage down at the bottom, and then I know
Are you talking about getting the output voltage?
getting the one that goes into the plus, getting the.
Right, we need this voltage, right? Well, look, if we have the voltage across this resistor, we have the voltage at the plus terminal, right?
Yes. But like, how do you get that from V2?
Here's V2, right?
Yes, sir.
Look, I'm not sure if maybe the drawing is causing a problem or what. If I have this circuit, make this 10 ohms, make this 10 ohms, and make this 10 volts, all right? Simple as possible. And I want the voltage between here and here. That would be 10, right? 10 times 10 over 20, right? Or it would be 5 volts. Do you agree with that? Agreed? All right, 5 volts. Now, I didn't connect anything there. But now if I put an op amp there and put it to the negative or positive terminal, it doesn't matter. No current flows there, it doesn't change anything. So the 10 volts here is the voltage at that positive terminal with respect to ground.
The 10 volts is not the 5 volts?
I mean, sorry, 5 volts.
Okay.
The 5 volts, the voltage across the 10 ohm is that. Okay?
Okay.
All right, that's my goal here, to make sure everybody sees this. Are you with me? All right, one more. Oh, boy, that quiz. I'm gonna go through I'm gonna ask you to do some of the problems that have capacitors. The only thing different is this. With capacitors, you have a complex impedance. Now you have minus J. You're gonna have a minus J over omega C.
Good.